Before we take through our worked case example in detail, we need to turn away from face perception, which is relatively easy to understand, to the more technical domain of language. This has been, as it says, the bloodiest battlefield. This is where the wars have been fought. The remarkable capacity of infants for learning language has played a major role in all theories of human cognition and development over the last 40, 50 years. Some things are quite clear, which is that when we are competent speakers of a language, we exhibit something called categorical perception. Now, categorization is a very general term, and all life distinguishes between predator and prey, toxin and nutrition. So when we use the term categorical perception, we're talking about something which is much more constrained in its meaning and has been developed within certain psychological fields. In order to demonstrate categorical perception, we need to show that we have bad discrimination when two things in the world, two stimuli, I don't like the term, but we use it here. When two stimuli lie within a category, they may be physically different, but because they belong to one category, we are insensitive to the difference between them. And good discrimination across categories, so if we have two stimuli which are physically as dissimilar as the other two, but they straddle the category boundary, then we tell them apart. And we only get variable response at the category boundary. Now, the specific categories that are clearly in play for speakers of a given language depend on the language, so they certainly can't all be built in. So in English, for example, we've met the distinction between p and b, which is a categorical distinction. There's no such thing as being halfway between. You're either a p sound or a b sound. But this changes when we go to a different language. In Thai, for example, we have a three-way distinction here between p, b, and b. I'm not sure you heard the difference there, but there was. So there's three categories in Thai. In English, we famously have a phonological distinction between an L sound, la, and an R sound, ra. Whereas in Japanese, these are variants, minor variants, of one phoneme. And so Japanese native speakers show insensitivity to differences that for an English speaker are quite clear. This is great fun when taking the mickey out of people's accents, but every language has these properties. The categorical perception of consonants has played a big role in this debate, and I just use consonants to illustrate it. For vowels, the situation is less clear. Some people will assume the categorical perception works the same in vowels as it does in consonants, but it's not clear that that's the case. We're going to see the results of experiments that demonstrate categorical perception in humans, and the same methods, when applied to some animals, have also produced results that look like categorical perception, even though this is highly implausible. Japanese quail, a little bird, for example, have been, it's claimed, found to demonstrate categorical perception with respect to a linguistic contrast where they don't speak any language. So there's some danger here that we need to be cautious in our approach. Just as we saw in the last example, in the last case we saw that adult humans are very, very good at discriminating human faces and very poor at discriminating monkey faces. Whereas at an earlier stage, 9-month-olds were better at discriminating monkey faces than their adults. So somehow the increased capacity to make fine distinctions in human faces leads to a loss of the ability to resolve differences in monkey faces. And we see something like this in language as well. And this then has become a site at which the arguments over the relative roles of exposure to the world and its complexity versus the inbuilt discriminative capacities of a person have been fought. Here are some data, for example, showing that at 7 months old, infants who are later going to grow up to be English speakers and infants who are going to grow up to be Japanese speakers show similar discriminative capacities in distinguishing ra from la. So at this age, at 7, a language-specific difference hasn't arisen. By 11 months old, however, the English learning infants are very good at making this discrimination, which is a phonological discrimination in their language, whereas the Japanese learning infants have become less sensitive to that distinction. So there's an apparent disimprovement in this contrast for the Japanese learning infants. And this is not something about the specifics of English and Japanese, because we can show English speakers going the same way. If we take a contrast such as the one illustrated, which I'm poorly equipped to demonstrate, between qi and si in Chinese, which is a phonemic distinction, once more we find at 7 months, future Mandarin speakers and future English speakers display the same sensitivity to contrasting stimuli, whereas by 11 months of age, the English learning infants have disimproved on this, while the Mandarin learning infants have improved on this, because the distinction is phonemic in Mandarin and not in English. So you can see there's something quite general going on here about the acquisition of categorical distinctions and the sensitivity to differences in physical stimuli. Now, as I said, categorization is absolutely fundamental to cognition. We are discriminative, as are all life forms. Categorical perception, as we're discussing it here, is a specific, limited set of phenomena that come within the world of a specific theory, and we need to distinguish the two. More technically, to demonstrate categorical perception, you must show insensitivity to discriminations among stimuli which lie within a category, whereas the same physical distance between the stimuli leads to a sensitive discrimination if they straddle the category boundary. So as we change the stimulus, morphing it from one form into another, there's an abrupt shift in the labels that people would place on it right at the category boundary. So we're going to use the pa-ba distinction in English because it's particularly simple. We'll bear in mind, however, that theory can blind us. It will be possible, as I'll show in the next slide, to construct stimuli which span the range from pa to ba and are created in physically equidistant steps. And with that, the whole investigation of categorical perception kicks off. But what gets lost there is that we know for a fact that English speakers use a great many cues to disambiguate consonants in context. They don't rely on a single cue only. We're going to look, however, at a single cue which suggests itself precisely because it's relatively easy to manipulate, so that we can create stimuli which are evenly spaced by some physical measure, and yet which, when presented to people, will elicit this kind of categorical response. When you produce a pa or a ba sound, there's a stop, the air is obstructed at the lips, and it's then released. Where they differ is what happens between that moment of release and the onset of voicing in the glottis, which is the periodic flapping of the vocal folds. On the slide, you can see a zoomed up view of the beginning of a syllable, and you can see the moment of release of the closure of the stop, and you can see that the vocal fold vibration kicks in afterwards, shortly afterwards. The distance between those two moments in time is called the voice onset time, VOT. I should have written it on the slide. Sorry, voice onset time. And now it's a very easy job to take a waveform editor and to create stimuli which have a long VOT, and they will always be heard as pa, and to create ones which have zero VOT, they'll be ba, and to create all kinds of intermediate ones, and to present them to people in various ways. You can present pairs and say, are they the same or are they different? Or you can present them one at a time and say, label this, is this a pa or a ba? At the right-hand side, you see the results from measurements done on this. And what you can see is the red line shows the result of the labeling task. For a negative VOT, that is one in which the voicing starts actually before the moment of release, they're all heard as ba. And for a VOT of 0, they're heard as ba, 100%. For a short VOT of 10 milliseconds, they're heard as ba. But then it changes. Around 20 milliseconds, we get 50-50 pa, ba responses. And once the VOT is 30 milliseconds or longer, they're all heard as pa. So that continuity and then a sudden change in labeling is one thing we're looking for. The blue data there show the correct discrimination in the same different paradigm. And what you can see there is that the percent correct discrimination among stimuli which are adjacent to each other on this continuum is very poor within category on both sides, but gets very, very good right at the same place where the labeling shifted at 20 milliseconds voice onset time. So this kind of simplification of the speech signal allows us to construct experiments in which we have fine control over the stimuli that are presented to people and to demonstrate, as this clearly does, categorical perception. Having demonstrated it, however, we need to be cautious here because, as I said, real speech perception depends on a multiplicity of cues. We have created an artificial situation here. In actual fact, people combine multiple sources of information and they make probabilistic judgments that are based on an awful lot more than the details of the acoustic waveform. They're based on context and expectations and all sorts of things. So it's an open question whether categorical perception, which we can demonstrate clearly in the laboratory, whether it's a good description of anything we do or not is another question entirely. Now, the next video is going to be a little bit longer than this, and it's going to work through an example based on a connectionist modeling paper that takes some results from infant development studies, which led to one kind of conclusion about built-in capacities. And they use connectionist modeling to reconsider what the underlying processes might be. This is the Schaffer and Marischal paper. It's available in Brightspace, and you should please read that paper carefully before the next video. In it, we'll see something like what we just saw. We'll see that there are some discriminations in a particular context that 8-month-old infants seem to be capable of making, while 14-month-olds are not capable of making. So once more, we see this pattern of an initial capacity for discrimination being lost as a result of increased learning. And the question that the paper revolves around is, how should one understand that? Should one suggest that there's one kind of processing going on earlier and a different kind of processing going on later? Has there been a qualitative shift? Or could one account for this shift using a single generic learning mechanism and have this apparent change in capacity be an emergent from a single homogeneous training procedure? So you should please read that paper before the next video.